I'm glad to introduce the first speaker of this morning session, which is Piero d'Ancona, and he will talk us about localization of eigenvalues for non-self-adjoint operator. So if you have any question for the one who is here in the room, you can just raise your hand and we'll give you the microphone. And the same for the online participant, you can just raise your hand virtually, and then you can unmute yourself and ask for any question to Pierre. Okay, so I think we can start, and please, Pierre.
Can you put the microphone here?
Sure.
So you can hear my voice.
Okay.
Okay, so it's a great pleasure to be here. So first of all, thank you to the organizers of this short but intense conference, and it's a great pleasure to see so many friends face to face after 2 years of COVID. So let's hope this is a good start of a new era. And so this is the title. I will talk about some results obtained in the last couple of years in collaboration with Luca Fanelli, Nico Michele Schiavone, and David Krecilik. The results are available on Archive and Press now. Okay, so first of all, some motivation, because this is a spectral talk in a, yes? It's off. Okay, good. Okay, so some word of motivation about the interest in spectral problems. This is a strictly spectral talk, but we all know that when studying dispersive equations, I mean, the asymptotic properties of solution are very strongly conditioned by the spectral properties of the main part of the operator, right? So if you consider a Schrödinger equation, or a wave equation, or any other actually evolution equation connected to some self-adjoint operator H, then the spectral properties of H have a strong influence on the evolution, of course. The main fact is that if you have bound states, which means eigenfunctions in L2, then immediately you can produce a solution which doesn't decay. And so you have to take care of this, exclude it by some projection, or possibly take it into account when studying the dispersive properties. And oh, by the way, I have this banner here, and I cannot see my slides, but maybe you can. Oh, nobody can see my slides. Is it possible to exclude this?
What do you want?
Okay. No way.
No.
Perché ti risulta?
L'ho fatto io? Okay. So again, consider the 1D Schrödinger operator, second derivative. It has no eigenvalues, no eigenfunctions, but it has a resonance at 0 because the function, the constant function 1 is in kernel. And so one effect of this is that you have a decay t to the -1/2, which is too weak for many purposes. If you perturb the second derivative with a non-exceptional potential, which means generically almost every potential with some decay condition, non-exceptional means that you have no bounded solution for this operator. So now 0 is no longer a resonance. Then you have a better decay, at least locally. So you need some mild weight. You have a better decay. So you really see the effect of bound states and resonances on the decay properties of the evolution operators. Okay. So it is clear that the spectral theory is a big part of the analysis of dispersive equations. And if you work in the setting of self-adjoint operators, you have a lot of results, of course. Almost everything useful is known. But in the non-self-adjoint case, there are many open questions. So this is a big field to explore. Okay. Okay, let me briefly remind the tools you can use to analyze the spectrum and exclude or project away the eigenvalues and resonances. Okay. There are several ways to analyze the spectrum of the self-adjoint operator. Of course, it's contained in the real line, this is for sure. And one way to split it, which is very useful from the point of view of perturbation, is in essential and discrete spectrum. So the essential spectrum is the set of points in the spectrum such that T-Z is not a Fredholm operator. Okay, this is one possible definition. And so the complement of this is a discrete spectrum, and we know that the discrete spectrum is made of eigenvalues of finite multiplicity, which are isolated. Okay, the neighborhood which doesn't intersect the rest of the spectrum. Okay, this is just to remind that actually there is no commonly accepted definition of essential spectrum. There are several reasonable definitions. So the two extremes are probably Cato's definition, who requires only T-Z to be not semi-Fredholm, which means that you have an index which can be plus or minus infinity, but either the kernel or the complement of the image have finite dimensions. One of the two, not necessarily both. Okay, and the other extreme is the Weil essential spectrum. So you require that T-Z is not Fredholm with index 0. Okay, and there are other splittings. For instance, this is also relevant. We could split the spectrum into the point spectrum and the continuous spectrum. This is also important from the point of view of dispersive equations. And typically, you're interested only in the absolutely continuous spectrum. And the definition is sigma p is just a set of eigenvalue, very simple definition. And the continuous spectrum is the set of the complement, which is the set of Z such that T-Z is injective and not surjective and has dense image. Okay? We are in a setting such that you don't have anything else. Okay, in the spectrum. Okay, so the point spectrum contains the discrete spectrum, but you have also other eigenvalues, non-isolated eigenvalues, and eigenvalues with infinite multiplicity. Okay. Okay, this is just to remind you with a very well-known picture of the spectrum in the self-adjoint case. And let us say something more. So we want to know where the eigenvalues are and if we can exclude their presence. So the nicest theory from the point of view is Liptering inequalities and Zwicker-Losenthum so on theorem. So let us briefly describe this theory. If you have a Schrödinger operator, we are still in the self-adjoint setting, so V is the real value, the real value potential. This is a convenient set of assumptions. It's not the only possibility, of course. There is no information here on the sign of the operator, so there is a negative part in the potential V. And so we require some mild integrability. In one dimension, the potential is L1. Essentially, there is always you can always admit a bounded part, but essentially L1 plus in dimension 2, n over 2 in dimension larger than 3. Okay, so the continuous spectrum in this case is 0 plus infinity. So this potential does not perturb the free operator dramatically. And you may have a negative part of the spectrum, which is form of discrete eigenvalues. And in dimension 1 or 2, this could be an infinite set of eigenvalues. Okay? So this is the most difficult case. The low dimension is the most difficult case. Okay, so the Lipp-Thirring inequalities say that the negative eigenvalues satisfy an inequality like this. So what controls the negative eigenvalues is the negative part of the potential. Okay, so you consider some LP norm with P equals to gamma plus n over 2 of the negative part. And this inequality controls some moment expression in the negative eigenvalues, the sum of some powers of the negative eigenvalues. This inequality is holds for gamma. Okay, for gamma larger than 1/2 in one dimension and positive in 2 or 3 dimensions. Okay, the case gamma equals 0 in dimension larger than 3 was known earlier, and this was called the inequality of the Zwicker-Lieber rendezvous. Okay? Okay, so what does this inequality tell us about the eigenvalues? If you can take gamma equals 0, then here you are just counting the eigenvalues, right? It is the number of negative eigenvalues. So that set of inequalities control the number of negative eigenvalues. I can rewrite like this. So this power n over 2 is not unexpected when you count eigenvalues, right, in dimension n. So this is a natural inequality. But maybe more interesting is also the fact that the Lipp-Thirring inequality, if gamma cannot touch 0, you still control the location of eigenvalues. Because if you apply this to one single negative eigenvalues, you know that it is contained in some disk, right? Because you have a control on its size. Okay. So you can rewrite like this. Each negative eigenvalue is controlled in size by this power of the negative part of the potential. In dimension 1 and 2, the available results are weaker. And you understand, of course, that it is also relevant to compute the sharp constants here, to have a sharp estimate on the number of eigenvalues on the precise location. Okay, so this is a beautiful theory, but what happens in the non-self-adjoint case? I would say that the only really general tool available is Weil's theorem, which says that the Weil essential spectrum doesn't change if you add a compact perturbation to the potential. So if you have a, sorry, this is still the, okay, sorry, this is, okay, so if you add any compact perturbation to T, the essential spectrum remains the same, okay? And you can also have a stronger version because, of course, compact perturbation is too weak. I mean, it's too strong an assumption for the case we're interested in, okay? Because generic potential, for instance, is certainly not compact, but actually you can do much better. So you can perturb your operator by some relatively compact perturbation. So it is sufficient to assume that this operator is compact, even if you multiply it by resolvent operator, because you see, this is one formulation, but essentially you're multiplying t plus 1 to the minus 1, this operator. So this is order 2, almost 2, compact with respect to the resolvent. Okay, so this result can be applied also to non-self-adjoint operators. And let me see the way you can use this information. Okay, in the non-self-adjoint case, the main tool to prove estimate on the size and the location of the eigenvalues is the Birman-Scwhinger principle. This is quite nice and I think quite easy to follow. So let me give some sketch of the main idea. So it says you're interested in locating the eigenvalues of some perturbation of your fixed reference operator H0. Okay. The principle says that Z is an eigenvalue of this operator if and only if -1 is an eigenvalue of this operator. So this is the resolvent of H0, and you multiply by A and B on the two sides. And you will recognize this kind of operator appears very frequently in resolvent estimates. And so it is sometimes called the Birman-Scwhinger operator. Okay, and the proof is quite easy. I mean, if you do, at least formally, it's very easy. Of course, you have to put the proper functional setting, but the proof is easy. I mean, if V, for instance, in this direction, if V is an eigenvector of the perturbed operator with eigenvalue Z, then consider the vector AV, apply this operator, and then just the very simple identity, you get this. So since this is 0, this is 0. So you discover immediately that if V is an eigenvector of the operator, AV is an eigenvector of this operator, which means that -1 is in the kernel, is in the spectrum, the point spectrum of this operator. It's an elementary computation at the formal level, and also the reverse implication is easy. So essentially, you reduce the analysis of the point spectrum of your operator to the analysis of a much simpler operator, because this is compact and I mean bounded in many cases. So and you just look for one special eigenvalue. Okay. So this is just for completeness. I show you briefly one proper complete version of the principle. Okay, this is one recent version by Hansman and Piero. So you have you are in general setting of Hilbert spaces. You take a self-adjoint operator. You call G0 essentially the operator. This and A and B are essentially relatively bounded operators. You define the Birman-Scwhinger operator like this, which you will recognize formally. You can simplify G0, and it is exactly A resolvent B star. And so the proper formulation is that if Z is in the point spectrum of the operator, then -1 is in the spectrum, the point spectrum of kappa zeta, the Birman-Scwhinger operator, and vice versa. Okay. And by the way, this formulation can give information also on the residual and the essential spectrum. So this is quite complete point of view. Okay, so now we see that since we have to go from this operator to this operator, now we're talking about resolvent estimates. So to bound this operator, and for instance, to say that this is so small that -1 cannot be in the spectrum, we need a resolvent estimate. Let me also briefly recall this fact that resolvent estimates play a role since many years in the field of dispersive equations. So already in Kato's theory, he showed that a resolvent estimate for an operator, this is a resolvent of H, is equivalent to a smoothing estimate for the Schrödinger evolution. Okay, and this is the standard definition of H smooth operator. So the thing to keep in mind that the resolvent estimate is equivalent to a smoothing estimate. And some examples are, for instance, if A is the multiplication by some function in Ln, essentially, then it is smooth with respect to the Laplacian. Also, x to the -1 in dimension larger or equal than 3 is a Laplacian smooth operator, Laplacian super smooth actually. And so the corresponding smoothing estimates are like this. So Schrödinger, the solution to the three Schrödinger equations satisfy an estimate like this or like this. By the way, for instance, you see to prove this is quite easy using the dispersive estimate for directly for the Schrödinger operator. Okay. Anyway, there are many results known in this direction. For instance, the classical theory of Hagelmann and Edermander says that this kind of operator is smooth, so you have some gain of regularity in the smoothing estimate, 1/2 gain of regularity. Kato, Yajima, and Sugimoto investigated extensively the operators of this form, and they got the general form of a smoothing of a delta smooth operator, like this. And also, let me recall the results of Benartz and Kleiderman, which reach the value 1/2 here. Okay. Anyway, so there are many results of this type. Let us now apply. This is just a recap of what we said before. So, using a Birman-Scwhinger theory, now anytime you have a weighted resolvent estimate for H0, you get some information on the location of eigenvalues for your perturbed operator. Okay. I'm not sure, but that Frank was the first to apply in the non-selfadjoint setting. I don't think so, but I mean, the most famous results come from him in this direction. Okay, and so let me show you the principle in action. Still in the setting, but so you can use it essentially in two ways, which are the same, but I mean, give a different kind of result. So suppose that you know a resolvent estimate, like one of the estimates I showed you before. Okay, so you have a resolvent estimate, a nice resolvent estimate, and maybe it is quantitative. So you know how the constant here. I mean, this is a bounded operator, and you know some estimate for the norm of this operator in terms of A and B. Now, suppose that the operators A and B are small in some suitable sense. It is sufficient to assume that this constant here is strictly smaller than 1. Then, of course, you have an inequality like this. So this applied to B is strictly smaller than B, and this immediately excludes that -1 can be an eigenvalue for this operator. Okay, so apply Birman-Scwhinger theory, and you have just proved that this operator has no eigenvalues. Okay, very simple. And let me show you another way to use the principle. Suppose instead that you know that your resolvent estimate depends on Z. Why not? It happens very frequently that you get Z-dependent estimate. Then, if you assume that lambda Z is strictly smaller than 1, this means that the operator has no eigenvalues, right? So the eigenvalues of this operator must be contained in the region where lambda Z is larger than 1. Okay? So you have a localization of result for the eigenvalues. Okay, so applying precisely this principle, several results have been obtained. So, for instance, in the case of Schrödinger operator with a complex potential, Davis and collaborators, and then Frank for any dimension, obtain a result of this form. The eigenvalues of minus delta plus B must be contained in a disk with this radius set to 0, and the gamma. Okay, you take the gamma root, of course, if you get a bound on Z, and the gamma must be 1/2 in one dimension, or any positive number less than 1/2 if n is bigger. There is a conjecture still pending, I think, by Laptev and Safronov, that gamma can be extended up to n/2, and but this is only proved in the radial setting. Okay. Oh, by the way, by now I should have convinced you that anytime you have a nice resolvent estimate, you have a result of this kind. And the result of Frank, for instance, is based on this kind of resolvent estimate, which is the uniform resolvent estimate by Koenig, Ritz, and Sauter. Okay. Okay, so now let me come closer to the main subject of the talk. You can do this for many operators, of course, not necessarily only the Laplacian. And one very interesting case is Dirac operators. The theory of non-self-adjoint Dirac operators is not so old, so still there are many open questions. Let me briefly remind you that the Dirac operator, first of all, is a matrix operator. Okay, so it's a constant coefficient matrix operator which acts on functions with values in Cn, which are called spinors sometimes. But the form is very simple. So you just have some constant matrices times the derivative, and you can have a mass term, which is another constant matrix. Okay. This is just a jargon to say that these matrices satisfy some anti-commutation relations. So they do not commute, but they have this nice relation. They are self-adjoint Hermitian matrices. And you have actually, this is a coordinate independent formulation, but you can also give explicit formulas, of course. But any set of matrices that satisfy this list of relations is good to describe Dirac theory. Okay, so for instance, one choice is this. This will be always called the mass. It can be any real number, but we take a positive for convenience. And so this operator is self-adjoint. The domain is what you expect, so essentially H1. And the spectrum is, depending on the mass, is two half lines or the entire real line in the case the mass is 0. Okay. Now we consider dV, which is a perturbation by a non-self-adjoint, non-Hermitian matrix V. Okay. Potential depending on the variable x L2 lock, but apart from that, for now, no assumption. And so to show you the precise form in 3 dimensions, you can take, for instance, this set of matrices, which is a standard set of Dirac matrices. In 2 dimensions, you have a 2x2 system, and these are called sometimes the Pauli matrices. And in 1 dimension, you also have a 2x2 system. Okay, so you can, in any dimension, you can find a set of matrices which satisfy this the set of anti-commutation rules. Okay, this is just to show you, but the exact form is not so interesting. The main fact that which is useful for Dirac is that if you take the square of this Dirac operator, you get a diagonal operator, which is a Laplacian or a Laplacian plus master. Okay, so in some sense, D0 is a square root, a non-commutative square root of the Laplace operator. And this is the main justification to introduce these operators, but maybe let us not talk about this here. Okay. So by applying Birman-Scwhinger theory to Dirac operator, when in Laptev-Feldreiter obtain a nice result in dimension 1. Okay. So take any matrix potential 2x2 in L1. Just assume that L1 norm is strictly smaller than 1, and then you get a bound, a localization result for the eigenvalues of the operator, which are contained in the union of 2 closed disks. Okay, and so these are the centers symmetric with respect to the origin. These are the centers of the disk, and these are the radius of the disk. And in a massless case, the spectrum is R. So you have no stray eigenvalues outside the real line. Okay, so nice result, quite complete. You might wonder about the sharpness of this condition, but certainly it's a simple condition. Okay, just a bound on the L1 norm of the potential. And so, as usual, this is based on a resolvent estimate. Since we are in 1D, this is especially simple because you have a very explicit computable forms for the kernel of the Dirac operator. And so you get a very powerful estimate from L1 L infinity of the resolvent, this is sharp. And so based on this and using Birman-Scwhinger principle, you get that result. Okay. So you try, of course, to do the same in a higher dimension, but this is a very lucky situation in 1D. In 2D or higher, you cannot have the reason. I mean, you can, if you try to take the square of this to reduce to the Laplace operator, you immediately see that you get different regimes for small z and large z. Actually, it's possible to convince that you can have an estimate like this from LP to LP prime, like the Koenig-Rützhauge estimates, if and only if P and P prime satisfies this condition. By the way, in Koenig-Rützhauge, you have 2 here, but now you have 1. So this forces n to be equal 1 in the Dirac case. Okay. Okay. So this way doesn't work for the higher dimension. Of course, there were a lot of studies in higher dimension, but the best Quentin could obtain was an estimate in an unbounded region, not I wouldn't call this a localization of eigenvalues, or rather an exclusion region for the eigenvalues. Okay, P is larger than n. So I mean, nice conjecture would be, for instance, that in dimension n, if the ln norm of the potential is small, then you should have localization or absence of eigenvalues. But I mean, it's far from what is known now. Similar results were obtained by Quentin-Tretter and Fanelli-Kriciric, again with unbounded regions. Okay. Now let us come to our result. You know the principle. We just start from a careful resolvent estimate. If your estimate is sharp enough, then you get good results on the location aggregate. So what is the resolvent estimate? So this is the spirit of our result. In dimension larger than 1, in the massive case, if V is suitably small in some norm, you will see the eigenvalues are localized in a compact region. Okay, so this is the analog of the Quentin result in dimension 1 to higher dimension. And in the massless case, the spectrum is precisely R. Okay, so this is quite satisfying. Let me describe the norms we use. So the space we use is a bit strange, but if you are familiar with Permander's book, it's something that, or some result by UNESCO and Koenig some years ago, 2005. It's not new. It's not a new estimate. So you consider, you fix a direction, for instance, a coordinate direction, and you take the L1 in that direction of the supremum in the other variables. Okay. And you do this for all directions. You can do any direction or just the coordinate direction. You get the same, essentially the same. It's just simpler to analyze. Okay, and of course, the corresponding norm is just the sum or the maximum of this partial norms. Okay, so this is our norm y, L1 and infinity. And so this is the precise result in dimension larger than 2. If the y norm of V is small enough, then we have a localization of the eigenvalues in in the union of 2 compact disks, okay? Exactly like in the case n equal 1. And this is the precise form of the centers and the radius of these disks. Okay. If the mass is 0, under the same assumption, then we have no eigenvalue. Okay, so the spectrum is exactly the real line. Okay, so this is a precise analog of the result by Quentin and others, but what changes is that we don't have it would be nice to have an L3 or Ln norm here, but we have this different norm, which is very satisfying. So let me briefly tell you. So what is the resolvent estimate used here? It is this kind of estimate in this space, which is quite natural, actually. So L1 in one direction, L2 in the other directions, okay? So the dual of this norm is the sum of the, sorry, maybe this will be the union. Okay, this is a precise the precise definition. Sorry, the sum is not here. Okay, let us look at the norm. So the norm of X is the maximum of this set of norms, L1, L2, and the dual is the infimum of all possible decompositions, okay, in L infinity L2. So, I mean, this is quite standard functional analysis. Okay, this kind of estimate cannot, I am pretty sure there is no way to prove this by multiplier method. The way to prove it, this is inspired by Hermander's approach to, principal value operators. Essentially, you have to work in Fourier space. So you, in Fourier variables, you divide into 2 to the power 2 to the n sectors. So you divide where the one of the variables is larger than the others, than the absolute value of the others, and then essentially you have to straighten. Okay, the Laplace operator -1, for instance, has singularity as an absolute value of psi, modulus of psi equals 1, okay, on a sphere. Then you have to take caps on the sphere, straighten it, and so basically you reduce to just division by psi in one direction. Okay, so essentially your Laplace operator is reduced to an integration, and this integration is what gets you from L1 to L infinity. So if you estimate the L infinity norm of an integral in one variable, you estimate with L1 of what is inside the integral. Okay, so this is, conceptually is very simple. Maybe I'm going to pick about it. It's a very simple idea, but to put it into practice, you have to, apply some Fourier analysis. Okay, once you have this, okay, maybe it's also worth to mention that you have a good resolvent estimate, quite sharp resolvent estimate of this form, okay, in these spaces L1, L2, with values N infinity L2. Okay. Let me mention also another group of results by this circular ideas. And some years ago with Luca and Federico and Renato, we obtained several estimates, several resolvent estimates, which the purpose there was just to get smoothing estimate for Schrödinger equations and then Striker's estimates. Okay, so we have not in mind spectral applications, but I think it was Luca who realized that actually why not apply those estimates also to in combination with Birman-Scwhinger to obtain some localization of eigenvalues. And indeed, you can get some results which are new. So the setting there was to use weighted norms for the potentials and to get a weighted norm smoothing estimate. So let me briefly tell you what is the setting. Okay, actually also these dyadic norms are not new at all. They appear constantly, but in a few results on Schrödinger equation, for instance, in Tataro, you can see it applies all the time. And so maybe start from this. So you divide the space into annually, dyadic annually. Okay, so x is between 2 to the j minus 1 up to 2 to the j. J can be also negative, so this is smaller and smaller when you approach 0. So this is a homogeneous norm. So you take the LQ norm on each annulus, and then you take the supremum over z, and you call this L infinity LQ. If instead of the supremum, you take the LP norm, a small LP norm of the sequence, then you call this LP LQ. Okay. So this is just one possible norm, which has a very precise homogeneity, so it's useful in this setting. Okay, so for instance, if you have an unperturbed resolvent Laplace operator, here, sorry, I mixed the notation. R0 is R minus delta. Okay, you have a uniform estimate of this. From the point of view of scaling, this is sharp. You see, so this is the beauty of this kind of dyadic estimates. So L infinity L2 weighted is estimated by L1 L2 also weighted. Okay. I think it's very close to sharp, this kind of estimate, as long as you consider radial estimates, estimate with norms, spherically invariant norms. Okay, and I think working a lot on this, I think that actually you could prove that the range of this operator is contained in C0 and 2, which means instead of L1, so I put the weight on this side. Instead of, sorry, L infinity L2, the weight, possible outcome of R0 are contained in decreasing to zero sequences. Anyway, okay. This is the starting estimate for the free operator, and this is the result. So in dimension larger or equal than 3, or maybe I should mention that this kind of estimate is not available in dimension 1 or 2. Okay, so if this norm, weighted norm, dyadic of the potential is sufficiently small, then we have again a localization result for the point spectrum, which is contained in the union of two compact disks. Okay. So now this is the weighted norm we use, and for strictly positive mass. Okay, another result you can get. I mean, all these results are very similar with each other. Okay, you have a condition on the potential, and you get some outcome on the point spectrum. So another possibility is that you have a norm of this form where now the dyadic part is contained in this weight rho. So take any weight rho which is in L2 L infinity, and so essentially, if this is sufficient, sorry, if this is sufficiently small, in this case you get that you have no point spectrum. And in the massless case, this condition can be replaced by the simpler condition weighted norm of V in L1 L. Okay. I think you get the spirit of this kind of results, right? And okay, I think I'm a bit ahead of schedule. That's inevitable, but I thank you for your attention. And,
okay, so thank you, Piero, for the. Okay, thank you, Piero, for the nice talk. So it's time for questions, both here in the room or online. So if you have any question, please. Nicola, okay.
Is it possible to construct potential to be a case for which you have embedded the environment?
The microphone, I should use the microphone or? I mean, this is a very good question, but I don't know. I don't know if there are results. Also for Schrödinger, there are not many results of the explicit results. Yeah, you have examples, but not many. I mean, I'm saying that for Dirac, I don't know. I don't think anybody has constructed. Possibly one can reuse the examples for Schrödinger, recycle them, but I don't know if anybody has tried. Outside, yeah. Yes, yeah, of course.
Other questions?
I just what's preventing you from establishing the resolvent estimates by multipliers? You said in the multiplier methods is not.
This is just my guess. I mean, because we use heavily Fourier transform, and we have to split. I mean, really the idea is quite simple. So, a resolvent operator in Fourier variables is division by a singularity on the sphere, right? Something which vanishes on the surface of a sphere. Then the idea is to straighten up the sphere. You can do by caps. When you straighten up, it's just Laplace operator becomes a one-order operator essentially, because it's just the division is by psi. Division by psi is just the integral, and so you get an L infinity L1 estimate, trivial. But then you have to put the pieces together, and I have no idea how to do this with the multiplier method, but maybe someone can do it.
Any other question?
Related to this question. In some cases, at least for the Schrödinger, once you have an infinity one, then you can switch to a two-weighted, which is weaker but not weak. So for a two-weighted, maybe there is some hope to work by intervention parts. So it is useless here other two-weighted definite, you bigger infinity one. To compute.
No, I think it could be useful. It could be useful, yes. No, I think it could be useful. I mean, in the end, you get less sharp result because I mean you get a stronger condition in the potential. That's it.
Other question here in the room? Since not, let's see if online, if we have some question online. Ci sono? Ma non ci sono. Okay. Okay, so if there are no other questions, we can thanks Piero again for his talk.
Thank you.